spend more money than it's necessary. Some people would like to know how many pounds everybody has spent. So let's do a quick poll. Who has got their host and everything for free? Oh, you can see around 5 people. People who spend around £10. Good. 20. 30. 40 pounds. More than 40. So, it's not a competition about who spends the most, okay? You can buy an old Mini or a Rolls Royce, okay? The people who spend £10 didn't get the same service are people who are spending £50, okay? So it's not a competition, it's better to be one way or another. But just to give you a feel, if you haven't already bought your domain, it looks like you can get it for free. For 10, 20 quid, you could do it if you really want. Okay. Some people say, why are we paying for that? It should be part of the fees. Okay. Again, it's a very small amount of money. For each course, you have some material to buy. You have some books. And the total in books is maybe more than what we have spent here. And also, people have different needs. Okay? If I give you a free hosting stuff, which is an old second-hand car, and your needs are much higher, you'd say that's right. Okay. So that gives you full freedom. And also, it's something that, in principle, you are going to keep for a certain amount of time. Okay? This host, at least the domain, it may follow you for your whole professional life. You are starting building a brand, building yourself, and if you are getting successful, you are not going to close down everything because IT Toolbox is finished. Okay? So it's getting started, and if it's going well, keep it open. Okay? But as you have seen, it doesn't cost that much. How much do I need to pay in order to have my blog on Google? It's free. It's free. What you need is to Google to get you in the first pages. Okay? To be at the end of the list is not very useful. How do you get Google to get you in the first pages? So it's indexing. So you want people to have link towards your blog. The more people who are going to link towards your blog means the more your blog is valued. Okay? If nobody is looking at your blog, Google is going to put you at the end of the list. There is no point, nobody is interested. However, if a lot of people are linking to your blog, it means they are interested. And the more important those people are, the better it is as well. If the BBC have a link towards your blog, it's a different type of accreditation that if your friend has a link towards your blog. Because the BBC has a lot of links towards them. Okay? So who is linking towards you is very important as well. Okay? And it's part of the e-commerce theme, and you will have a lecture on that as well. Okay? So you don't need to spend money in order to be on Google. Obviously, by spending money, you can go a bit faster. There are tricks, and we will tell you about that as well. And you are not going to have any other cost associated to IT Toolbox. Okay. Okay, so that was my feedback about last week's activity. So basically, I've been very pleased by people who did the activity. Only a handful of people I emailed to, because basically their link they provided was not correct. I clicked on it, I couldn't get their blog, so I cannot mark you. So please, I emailed you. Any of you is in the room? Yeah? Okay, so some of you have received an email from me saying, sorry, you don't have the 4% yet, you need to provide me a valid link to your blog, submit again, and if it's fine, you get the 4%. Yeah. So that's the advantage of submitting early. So the topic of this week is linked to hardware and also the numbers that computers are dealing with. Okay. So here is a memory card. Yeah, you have seen some of these, and you can see there is a number on it, 512. Interesting number. No? You have a memory card, another type, 1024. I will ask you a very difficult question. How many grams do you have in 1 kilogram? 1,000. Excellent. How many meters do you have in 1 kilometer?
1,000.
How many bytes do you have in 1 kilobyte?
1,024.
That's interesting. Okay, so there's something wrong or something strange, and part of the answer will be given today. Okay, it's not working the way we live the normal life. Why 1024? Why 512? They are not the type of number we use usually. Here is an error message, and you can see this number BFFA 3 zeros and an F. Okay, that's again a number that computer scientists must be able to understand. Okay. So our world is analogous. Do you understand what analogous means? So analogous means is continuous. When you have an analogous clock like this one, the big hand is moving in a continuous manner. Okay, it's not. You will go from 3 seconds to 3 a little bit, a bit more, and you are going to 4. Okay, it's not 3, 4, 5. Any value is going to be represented on that type of watch. Okay. So if we look, for example, at the temperature in a place, so somewhere in England, in October, here you have the temperature, and you can see that the curve is continuous. So at some point we are at 2 degrees, and it's moving slowly towards 3, 4, and so on. It's not jumping from 2 degrees to 10 degrees. Everything is continuous. Yeah? You are going through every single value. Same thing about the time. Okay? Here, we are not collecting the temperature every minute. At every single instant in time, we know what the temperature is. Okay? So that's our world. It's analogous. Things are changing in a very smooth manner. It's gradual. However, we have also the digital world, okay, which can be represented by that clock. Okay, so your seconds is here 36, then it's 37. It's never going to 36.5. Okay, so somehow there is a loss of information. Okay, we are only taking information at given values. So that's the digital world. So these values are called discrete, and they are not continuous. So you have jumps between different values. So here, if we look at the temperature again, so the temperature here is digital. So we have values only for each degree. Okay, we jump from 12 to 15. There is no value in between. Okay, it's just a jump. That's the digital world. The time also here is digital, is discrete. We are taking values every 12 hours. Okay, we are jumping to every 12 hours. We are not looking at what is in between. Okay, always very fixed values. That's the digital world. Just a question for people who have been very you have looked at that curve. Why is the curve going up and down all the time? You know, it's here, it's going up, down, up, down, up, down. It's an interesting pattern. Do you know why? Can you guess? Exactly. So we take the time every 12 hours. Here it's night. Here it's during the day. Okay? So in general, it's cooler at night than during the day. It's not always the case, but it's a general pattern. And so part of the digital world, we have the binary information. Okay? A binary means that the world can have only two values. So in this case, is the temperature cold or mild? If it's cold, we give a value of 0. If it's mild, we give a value of 1. Okay? So you can see that, again, the precision have lowered quite significantly. But using that, we see even better the pattern between night and day. Okay? Now it's very clear. While here, because we had all these different values, it was not as clear. Okay? So moving to a binary world sometimes allow you to interpret better the data. You lose a bit of information, but you get a more general view of your data. So, as I said, the binary world is one case of digital world. Okay, so who has ever used a long play? A disc, a record? You know this black one? How many of you? Oof, not many. So, if you want to listen to music, you have the choice between using an analogous disc, this long play disc, or a digital disc. Okay? Which one is best? Analog or digital?
Yeah, depends which measure you're against.
Analog is better.
Analog.
Analog is always better because digital is always simplifying the values. Okay? So if the value was 2.3 in analog, in digital it's going to be 2. Okay? So you are losing accuracy in the digital world all the time. Okay? So analog is better. So, however, the technology is a bit different. So you have a silicon, and you have this pin following, and depending on the depth, it will give you a different note, okay, a different sound. And so the value is continuous. Any value is possible, okay. On the other side, you have numbers represented by these little holes and bumps. And what is a bump is going to be 1. A hole is going to be 0. Okay? So it's back to the digital world. And so the good thing is analogous is continuous. Any value can be there. Digital, you have simplified the data. However, in the analogous world, if you put a bit of dust on your disk, you are going to potentially destroy your data. Okay? So the first time you are listening to an analog disk, the quality will be the best ever. The second time, it will be a bit less good. And after a while, your digital disk will be much better. Okay? So digital is better for the long term. Okay? Because you cannot alter the data. It's either 0 or 1. Okay? So you can add a bit of dust, it will be either 0 or 1, it will still be a bump or a hole. Okay? In the analogous world, any little problem and you change the value. Okay? So that's why now we have moved everything to digital. But for the purists, and there are purists in music, there are purists in photography, they prefer the old systems. Okay? because initially, when the data is fresh, it's of better quality. There is no doubt about that. That's what physics tells you. But after a while, digital is better because there is no degradation in the data. Okay. Also, the systems are much simpler. You know, if you want to read digital data than analogous data, you have digital circuits which are extremely cheap, and on a digital disk you can store much more than on an analogous one. Okay? So the world is now digital. There are some people trying to stay in the analogous world, but it's definitely not the future. Yeah?
Does the same concept apply to telecommunications?
Yeah, exactly. Of course.
So you have IGNs and analogs. How do they? Do you still think analog is better in that case?
I mean, analog is better because you have the data hasn't been simplified. Okay. However, as soon as something wrong is happening, there is some noise on the line. There are some interferences. Analog is going to go down. Digital is going to stay the same, if the noise is not extreme. Okay. So digital is very stable. Analogous, when everything is perfect, nice, much better. Unfortunately, our world is not very often in that case. Okay? So that's why we are moving to digital in every single topic. Yeah? Okay. So if we look at the digital world, there are different types of numbers. So the numbers we are using every day when we are doing our shopping is the decimal world. Okay? So we have values using digits between 0 and 9. Yeah? We have spoken already about the binary world. Okay? There are only two types of digit values, 0 or 1. And then we have the octal world. So I don't know if many of you is familiar with this world, but that's a world that computers is using. And it's base 8, so there are only 8 types of digits. So you go 0, 1, 2, 3, 4, 5, 6, 7, and the next number is 1, 0. We'll see why later. And then you have the hexadecimal world, which is also highly used in computers. So instead of having a base of 10, so 10 different digit values, now we have 16. Okay? So you go from 0 to 9, and then you have A, B, C, D, E, F. Okay? And when you have reached F, you add an extra digit. Okay? So if you want to write 17 using hexadecimal, you are going to write 1, 0. We will look at it again. Okay. So another concept which is very important when we are looking at numbers is what is the least and the most significant digit. Okay? So the least significant digit is the one to the right, and the most important digit is the one to the left. Okay? So if you are going to buy an item, and it costs 952 pounds, what is important, it costs 900 something. It's not that it's important that it costs 2 pounds and a bit and something else. It's the 900 which is really important. Okay? So this concept is going through any type of numbers you are going to be using. When we speak about binary values, it's very much used in computers because it can be represented by a circuit, and 0 means the circuit is off, the light is off, on, the light is on. There is electricity. Electricity, no electricity, 1 or 0. And that's how you build a computer. All the operations are based on that. Okay? So let's look at the first 15 values. To count from 0 to 15, we've been able to do that for a long time. When you are going in the octal world, as soon as you are reaching 7, you have to add an extra digit. So the first digit you have is 1, and then you have a 0. So you have 1, 0, 1, 1, 1, 7, and the next number is 2, 0. Okay? Obviously, when you are in the hexadecimal world, you can go up to F. And the next value, which would be 16, would be 1, 0 again. Okay? So, something which is very important is that decimal is based on a base of 10 values. Octal is based on 8, hexadecimal is based on 16, and binary is based on 2 values. Okay? So you can see how you count in binary. First you have 0, 1, then you have 1, 0, 1, 1, 1, 0, 0, 1, 0, 1, and so on. Okay? You get the concept? Each time you have finished with all the values, you add a 1 further left, and you replace everything by 0. Okay? That's the way you count in binary. So when you have a base like the binary one, where you have only 2 values, to express a number, a decimal number like 15, you need already 4 values. You need 1, 1, 1, 1. Okay? However, if you are using a base of 16, like hexadecimal, you just need 1 character to represent your number. Okay? So you can imagine that when you have huge numbers, in binary, you are going to fill in pages and pages with 0 and 1s, whereas in hexadecimal, it will be a very compact representation. Okay? So let's speak about the ASCII code. Okay, so it's an American standard for exchanging information, and it's used in order to exchange alpha-decimal characters, so letters and numbers, and it's a 7-bit code. Okay, so in binary, it means you can have up to 7 values. Okay, which means that in total you can go from 0 to 127. Okay, you have 128 values in order to code any values of the Latin alphabet plus the numbers, plus a few special characters. However, 7 is not really a number that computers like. Okay, we have already spoken about octal, which is 8, and hexadecimal, which is 16, which is twice 8. So computers quite like the number 8. So in practice, the ASCII code is coded in 8 bits. The first bit, the most significant, is always 0, because we don't need that much information. And this 8 and 8 bits is called either an octet, which is more the Greek octet for 8, or the byte that we are more familiar with. Okay, so when we are getting some memory, we are getting it in bytes, kilobytes, megabytes. Each time it's 8 bits. Okay. So here is the ASCII code, the first half. Okay, so if you want to write 4 in ASCII code, here is the 7 bits. You need to write 110100. Okay, that's in binary. If you wanted to write it in hexadecimal, it would be simply 34. Okay, so here we have some characters, the numbers, and here we have the letters. So we have the capital letters and the small letters as well. Yeah, so that's the code for the ASCII code that is used all the time by computers. So when you want to send a value, you need to specify which base are you using, binary, decimal, hexadecimal, or other, and that will represent the character you want. Okay. So you can imagine that if you are doing some telecommunication operations, it's better to send 2 values in hexadecimal than 7 in binary. On your broadband, you have much less to send. Okay. And obviously, the world is a bit larger than the world using Latin alphabets. We have already mentioned that during the lecture last week. So there is an extension of the ASCII code, which is called Unicode. Okay, so it's a universal code, so that you can deal with many world languages, and that's what has superseded the ASCII code. So, for example, if we want to use Arabic characters, we'll be using codes between 0600 and 06FF using hexadecimal. Okay. So now we are not using 7 bits anymore, we are using 16 bits. So we have many more positions. Actually, we have 65,536 positions in order to code characters. So let's have a look at the table. Okay, so here you have the code for all the characters. So here we start with the Latin alphabet. Here we are moving to still Latin. And there are many strange characters that I don't know. So here we are moving to Cyrillic alphabet, Armenian, there's some Hebrew, some Arabic, some strange stuff. Maybe someone knows what it is. So it looks like here we have some Bengali, so you have all languages from the subcontinent as well. Malaysian. If you find one you like, just tell me. Tibetan. So you can see that now the code system is very much international. Okay, from the initial small group which allowed you only to code the Latin alphabet, now we are going through all the alphabets, hopefully all the alphabets in the world. Chinese is not using an alphabet, so Chinese is not there. They are using ideograms, so it's something different. Okay, let's go back. Okay, so let's look at now the power of 2. Okay, let's see how the mathematics are. So what is the value of 1 at the power of 2? It's 1. 2 at the power of 2, 4, 2 at the power of 3, 8, and so on. Okay, so here we have the power of 2. Why 2? Because when we are working in binary, we have 0 and 1. So each time we add an extra digit, we are adding a power of 2. Okay? And what is very interesting is that when we have 2 at the power of 10, we get a value of 1024. Okay? So it's quite nice because it's 10, which is a nice round number. and it's 1024, which quite close to 1000. So we are going to call that in computing science a kilo. Okay? So a kilobyte is 1024. Okay? So it's 2 at the power of 10. So that's where the 1024 is coming from. Here we have the 512 that you can find as well on some memory card, the 256 and so on. The numbers are coming from there, okay? Because everything is based on the binary numbers and power, and therefore because of power of 2. If we carry on, okay, 2 at the power of 20 is 1 million and a bit more. Okay? So it's not 1,024,000. It's a bit different. Okay? So again, the numbers are a bit different. But we are going to call that 1 mega. Okay? 1 megabyte is actually 1,048,576 bytes. Okay? It's not 1 million. So what we call a kilo in computing science is 2 at the power of 10, which is 1024. A mega is 2 at the power of 20, which is a bit more than 1 million. A giga is 2 at the power of 30, which is a bigger number. And then we are going to tera and so on. Okay? So now that we have those numbers in our head, we can conceptualize this hexadecimal, this binary, but we like decimal numbers. Okay, that's what we can relate to. So there are methods to convert a number from whatever base to decimal. So let's look at an example. I think it's easier to see it that way. So let's say that we have a number which is 110101, and that's a binary number. Okay? And we would like to know how much is it in the decimal system. So it's very simple. Each number, each digit has to be multiplied by a power of 2. Okay? Because we are in the binary world. So the 1 will be multiplied by 2 at the power of 0, which is equal to 1. The 0 will be multiplied by 2. The 1 multiplied by 4. 0 by 8. 1 by 16. And 1 by 32. So you add up everything. And so this number in binary is equal to 53. Okay? So it's quite straightforward. You can do that on the back of the envelope. So that's when you want to go from binary to decimal. So you can see that there is a formula, and the formula is the same whatever base you are using. So if, for example, we have this number in hexadecimal, we are going to do the same, but using the hexadecimal base. So we are going to multiply 4 by 16 at the power of 0. 16 because we are in hexadecimal numbers. Yeah? C will be multiplied by 16 at the power of 1. 9 will be multiplied by 16 at the power of 2, and E will be multiplied by 16 at the power of 3. So if you want to get the value in decimal, you are going to add up all those numbers, and you are going to get 59,844. Okay. So initially we had only 4 digits, now we have 5. So the higher the base, the more compact the writing is. So sometimes you want to do the opposite. You want to go from decimal to another base. For example, you want to go from decimal to binary, because for your problem, the computer needs to calculate in binary numbers. So let's try to convert 41 in decimal to binary. So what you do, you need to be able to divide by 2. Okay? That's very advanced mathematics. So 41 divided by 2 is 20, and the remainder is 1. You divide 20 by 2 again. Remainder of 0, and you have a 10. You divide the 10 by 2. It's equal to 5. 5 divided by 2 is equal to 2, and there is a 1 remaining. Eventually, you divide 2 by 2, it's equal to 1. Now you have 1, you cannot divide anymore by 2, so you have finished your set of divisions, and you have your answer. So your most significant digit is the last one, and the solution, you read it from the end. So the solution is 41 in decimal is equal to 101001 in binary. Okay? And then you may be interested in going from one base to another base, which is not decimal. So you have to do the work twice. First, you go from your base to decimal, and then from decimal to the new base. Okay? So same concept as what we have seen. Obviously, you have many tools on the internet which allow you to do the same thing. So if you type a number, it will tell you in an instant what is the value in hexadecimal and in binary. Okay? So you can type in whatever part of the screen. So if I type in binary, I will get decimal and hexadecimal. Okay. So some of you may be interested in putting that on their web page. So it's not something that WordPress is going to help you to do. But if you want to add a little calculator like that on your WordPress environment, you will need some extra tools that we will see in the near future. Okay, so now that computers have numbers that they can work with, computers are essentially glorified calculators. They spend their time mixing those numbers and having some logical operations on them. Okay? So here is a set of standard operations that you need to be aware of, and that we are going to see into details. So you need to remember, guys, a bit lower the noise, that computers are really pieces of electronics. Yeah? And they are pieces of electronics where there is current going through electronic components. Okay? So all this logic is called the logic which is performed into gates. Okay? So you have electronic components, and usually you have one or two inputs, and depending on the inputs, you are going to get a given output. Okay? And so you can think about it as a device with two inputs. Here we are going to have let's say an electronic device which is going to decide if a fan should be switched on or not. Okay? And the logic that this piece of equipment is going to use is, okay, if it's hot, and at the same time it's sunny, I want the fan to be turned on. Otherwise, I don't want the fan. Okay? So you have this piece of equipment, this green box, and you have two inputs. One telling you if it's sunny or not. So if it's not sunny, it's a 0. If it's sunny, you get a 1. And 1, according to the temperature, if it's cold, you get a 0. If it's hot, you get a 1. Okay? And in this case, if both give you a 0, the outcome is 0. We don't want to switch on the fan. Okay? If we have a sunny weather, so one of the inputs is a 1, but still it's cold, so the other input is going to be a 0, which means that at the end we keep the fan switched off. So the output is 0. And finally, if it's sunny, one input is 1. If it's hot, the other output is 1. We have two inputs which are 1, which means in this case we want the fan to be on. Okay, so you get a 1 at the end of the process. So such a gate is called an AND gate. Okay, when both conditions are true, it's going to be on. If at least one of them is not true, it stays off. So each gate is associated to what is called a truth table. So according to my inputs, so if I have 2 0 as an input, what is going to be my output? Okay, so that's the truth table of each gate. So if we look at the AND gate, that's the one we have been looking at for this fan example. If both give you a 0, the output is a 0 as well. If you have a 0 and a 1, it stays off. If you have a 1 and a 0, it's off. However, it's both are on, it's a on at the end. Okay? So that's the AND gate. So if you want, you can think about it as a circuit with two switches. When the two switches are on, the light is going to be on. If any of the switches is off, the light stays off. Okay, so that's the AND gate. But you have another gate which is the OR gate, and the logic is a bit different. It's going to be 1, the output is going to be 1 if at least one of the two switches is on. At least one. So if you have 0 and 0, it's going to stay off. If you have 1 on 0 and 1 on 1, you get 1. It's going to be on. Similarly, if the first one is 1, the second one is 0. And if both are on, the output will be on as well. Okay? So that's the OR gate. If any of the switches is on, the light bulb will be on. So you can see it's a completely different logic, the AND or the OR. You have also the XOR, which is the exclusive OR. One of the two switches has to be on, but it cannot be the two of them. Okay? So if both are on 0, the output is 0. If one of them is 1, the output is 1. But if both are on 1, the output is 0. Okay? So again, we want one switches to be on in order to get the light on. If there are none or both, it stays off. We have a simpler gate, which is the NOT gate. And basically it's inverting the value of your input. If you are inputting a 0, the output will be a 1. If you are inputting a 1, the output will be a 0. So it's a bit of a strange shift, but when you switch on, you get the light off. And when you switch off, you have the light on. Okay? And then you can combine things. You can have the not and. Okay, so the table is the same as the and, but then you put the opposite. So it's the opposite of the and table. Okay? So which means when you have 0, 0, you get 1. When you have 0 and 1, you get 1. 1 and 0 get 1, but 1, 1 you get 0. So it's basically the same table as the and then you apply a not. Okay? And obviously you are going to get the nor, or the not or, which is going to give you the opposite result of a standard OR gate. So computers are basically based on that. The hardware, what you have inside your microprocessors, is those gates. Okay? You have current going through it, and all those gates allow you to do complex calculations. Okay? So if you want to study a bit further this logic, if you are excited by logic, you can build circuits yourself. So you can have your switches. You can combine stuff. No. We need a light. And now you can try your system. And you can create your own table, which may, and since here we are combining two gates, we are going to get results which are in none of the gates we have seen so far. Okay? So think about the computers as millions and millions of those gates all connected together. Okay? Okay, so we have the concept of gate. Now we need the concept of a bit of arithmetics. So computers, they really like additions and multiplications. Subtraction and divisions are complex, and they manage to find ways of doing it as multiplication and additions. Okay. So when you are adding two binary bits, it's very simple, and we have seen that before. You are adding 0 and 0, 0, 0 and 1 give you 1, 1 and 0, 1, and 1 plus 1. You have, you carry out 1, and you have 0. Okay, so that's the basic arithmetic for the addition. So you can use that for larger operations. So you can add up two longer numbers written with bits, and you get those results. Okay, using this same concept. So for example, here 0 plus 1 is equal to 1. 1 plus 1 is 0, and you carry out 1. So now we have 1 plus 1 plus the 1 which was carried out. So it gives you 1, and you carry out an extra 1. So now you have 1, 0, and 0 is equal to 1. 1 and 1 is 0, and you carry out a 1. Okay? So if you convert it to decimal, you can check that the calculations are correct. So the first number was 12 in decimal, second number was 17, and the third one was 29. So you can check that your addition has been successful. The multiplication is very easy. 0 by 0 obviously is 0. 0 by 1 is 0, and 1 by 1 is 1. So when you have larger number, you do the multiplication the standard way. And obviously each time you move to the next digit, you shift everything to the left, and you get your standard product. Just need to remember that 1 plus 1 equals to 1, 0. And again, you can check using your converter that if you use those numbers in decimal, you are going to get the same result. Okay, so that's what I wanted to tell you so that you have a better understanding about how computers use numbers and a bit about the logic. Okay, I mean that's really the fundamentals, and when you are using components using strange numbers, you have a better understanding where they are coming from. So now I would like to look at the architecture of a typical computer. So first of all, you have a key unit, which is the arithmetic and logic unit. So that's what we have just seen, how to do mathematics, how to do logics with numbers, okay? With all those binary numbers. So this unit is called the ALU. So that's a key component of your computer. Another important unit is called the control unit. Okay? So the control unit is going to tell the ALU what operation to perform. Okay? And these two units are what is called a CPU. Okay? So you must have seen this word before. It's your central processing unit. Yeah? That's basically the chip, which often has Intel inside. Okay, so that's where all the clever stuff is happening. All the calculations and what is the order of the calculations, where to get the numbers from. So where are these numbers? In some kind of memory. Okay. So a typical memory is your RAM, okay, so that's your fast memory, which is very close to those units. So getting the number from there and writing number there is very quick. So that's why if you have a computer with a large RAM, they will appear very fast, okay? So these days we are speaking about gigabytes of RAM on a fast computer. Yeah? But your memory, the data can come also from, for example, a hard disk or from a DVD. But if the computer has to look for the data there, it takes much more time. Okay? It's not as fast. And you can have external devices like your USB key. And again, it's slower. You are getting further away from the center unit of your computer. So in order to do this computation, you need obviously all those numbers which are stored in some kind of memory. You need some input device. So typically it will be a mouse, a keyboard. It can be some kind of sensor. Okay, depending if it's light or day, it may send some instructions. So it's the control unit which, according to this input, will look for the right data and will give orders to the arithmetic and the logic units to perform the operations. Okay. Then the control unit is taking the information back and will be outputting it on your output device, such as your computer screen, your printer, and so on. Okay, so that's the basic architecture of your computer. That's the basic architecture of your laptop. That's the basic architecture of your mobile phone. So now I would like to do the last half an hour, what I call a PC autopsy. Going to become bloody. So I want to explore the core components of a PC. So I brought a PC, and we are going to open it up and look what is inside. So who has already done that? Open a computer. Who hasn't done that? Somehow, some people are missing. So I'm going to need 2 volunteers. One who knows what he's doing, or what she's doing, and one who is just discovering and doing it for the first time. Okay? So who would like to come? So you have done it before?
Many times.
Many times, excellent. So and someone who hasn't done it? Who has never done it and would like to have a closer look? Please. It would be nice to have a lady for parity. Come on. Who would like to do it? Yeah. What's your name? So we have tuba and ask. Excellent. Okay, so they are going to dismantle that. We have a webcam here, so we are going to display on the screen what's going on. I hope they will not break anything, but we have an insurance, so that's okay. And we are going to look at what components we have in that box. So we want to know where is the RAM, where is the hard drive, where is this microprocessor, are there optical drive, what are the input-output devices, the monitor, we don't have a monitor, where is the motherboard, and a few cards, okay? So, which one?
Yeah, it's now.
Yeah, here we are. Oh, there is nothing coming. Okay. So first we want to open the box. Yeah. There are a few screws. Yeah, that's fine. That's sliding. Excellent. Yeah. Okay. Here's the beast. Yeah. Okay. No, that's okay. So we are going to get, what do we get first? The RAM? Can you spot the RAM? Okay. Yeah, you can do it. Yeah. You get the RAM.
That is not yet one.
On the left, here. Excellent. Let's look at it. Okay, so we can see some chips here. Okay, so that's our RAM. Any indication about how much there is? 1 gigabyte. Okay. Excellent. And there is a second one. A third. No. There are 4 gigabytes of RAM in that machine, which is decent.
Yeah, 442 disks.
Yeah. What else can we get from that? Is there a hard drive? Yeah, on the side, it's too difficult to get out. Go for it, go for it. Okay, so we are going to get rid of one of these. This one is let's go for the microprocessor. What is that? Let's go whatever you want. So we have the fan. The whole green bit is the motherboard. So that's the power supply. And we have slots for graphic cards and TV cards. And that's you very much for your help. Yeah, so this computer has proved to be a tough cookie, I think. An old generation, and we didn't manage to get out everything we wanted. But on your way out, if you want to have a closer look, you are free, and I will guide you towards the component. So they managed to get the RAM out. Okay. So what is very important for the RAM is the speed. Okay, how fast the information can be accessed. So it's usually in megahertz, and the size. So now we are speaking about gigabytes. Okay. There is the hard drive, and you have the external, the internal, and the latest technology, which is the solid state. You have the CPU, okay, so the central processing unit, and we have said that all the calculations were happening there, but that's where the control unit is as well. Guys? So in the CPU, again, what is very important is the speed, okay? How many calculations can be done by seconds? Okay? You want millions of operations to happen in 1 second, okay, when you are buying a computer. You may have multi-core computers, so you will have several of these units. So having much more calculations happening per second. Obviously, you have some kind of power supply. We can have an optical drive. So you know all about compact disc drivers, DVDs, and now we have Blu-ray discs as well. So that's the DV-ROMs. And we have input-output device, keyboard, mouse, touchpad, a webcam is also an input. Okay, so it's information which is going inside the computer, and we can act according to what we are getting. The outputs can be speakers, guys, a monitor, a printer. We have graphic cards, okay, because you don't want your microprocessors to do all the computations for the graphic display. Okay, now things are getting all in 3D with this million of colors. It's a lot of operations. So usually you are going to use a specific device, a graphic card, which is going to deal only with that part of the job. Okay? And you have different types of graphic cards which are with different characteristics. Then you have the type of monitors. And you have the motherboard. Okay, this green board where everything is plugged in. That's where your microprocessor is. That's where your RAM is plugged into, where your cards are going to be plugged, and obviously you have a place where you are going to plug the power supply. Okay? So basically everything which is on the motherboard will interact very quickly. As soon as you go outside of this space, things start going very slowly. Okay? Getting data from a hard disk, a USB key is very slow. If you manage to work with all your data in your RAM, computations will be very fast. We have also something called the BIOS. Okay? So that's again electronic device which is going to configure and test your hardware. And it's what is going to load your operating system. Okay, so if you are getting a computer which hasn't been installed with any operating system, at least you will have a BIOS. Okay, so that's the key to start using your computer. And it's checking that all the hardware is okay. Okay, so when you are switching on your computer, initially you have a black screen, and you have some lines appearing in white or black. That's the BIOS doing its work. And then it's launching Windows, Linux, Mac, or whatever system. And obviously you have the case, and you have cooling systems. So the most typical is the fan, and that's what we have here. But nowadays we have microprocessors which are running faster and faster, more and more operation per second. We have multi-core processors, okay? All that generate a lot of heat. You have noticed that when your computer, your laptop is getting hot, everything slows down and it even stops, okay? So if you want to have a very performing computer, you need to keep it cool. And nowadays, very often the fans are not enough. So you need something with a water cooling system, okay? So that's the next generation that the most advanced computer have. You cool down everything with water. Obviously, you are not going to mix water and electricity. Yeah? So everything has to be really well compartmented, but that's what you need in order to cool down very powerful machines. Obviously, you are going to get some kind of network card, sound card, and so on. Okay, so now we are going to speak about activity 3, which is due next Wednesday. Okay. So that's the IT Toolbox philosophy, okay? People have a computer. There is one component which is broken. They build the computer. 99% of it is still good, okay? So if you go to a skip which is full of old computers, if you select your PCs correctly, you will get your brand new computer. Okay? So that's what we want to do in IT Toolbox. Yes, pull down a little bit. Guys, can we finish this lecture? Okay. However, we have some health and safety issues, and if any of you will get injured in the process, I will have troubles. So we are going to do the next best thing. Okay. You are not going to buy, not quite. So you are going to get, imagine that I give you £1,000 each. You have the internet, and I'm going to ask you to build your own computer. You are going to buy each individual component in order to build a computer. And each component should be chosen with care. Why are you going to choose that RAM? Why are you going to choose that card? Okay? So depending on the application you have, you will choose one component or another. Okay? If your aim is to have a machine which is designed for video games, you would want the fastest graphic cards. You want maybe the best sound cards as well. Okay? However, if you are thinking about applications which is more towards quick connection with the internet, what is important is more the connection cards, and the graphic cards is maybe not that important. Okay? So you have a budget of £1,000.
Does the budget have to be 1,000?
Around 1,000. Okay? Because prices are changing every day. So you may build something for 1,000, and when I will check, it will be worth 1,100. That's okay. Okay? But if it's worth 3,000 or 5,000, it's not going to be okay. For 1,000, you can get a top machine, but it's not going to be top in everything. You will have to make choices. Okay? And the choices have to be guided by your application. Why are you making those choices? So you have to explain what kind of computer you want, what is going to be the application of your computer, the main one, and then each time you are making a choice, explaining why it's positive for that type of application. Obviously, I will ask you to do a bit of mathematics as well. Okay. to demonstrate that you have an understanding about those numbers. Okay, so you will need to do some conversions between binary numbers and hexadecimals and so on. And also, as usual, I want you to do a bit of thinking. Okay, so I will ask you to compare 3 computing systems. So a typical desktop computer, as you can find in any lab at the university, a smartphone, and an ATM. Okay? You can use the one which is on the car park. So you have 3 computing systems which have obviously similarities and differences. And I want you to think about those 2 aspects. What is similar, what is different.
How far can we go?
Excuse me?
How far can we go?
I will ask you a few points. Okay, it's not. I'm not asking an essay. I will ask you 3 to 5 points of similarity and differences. Okay, so best of luck. I hope I will get it next week and you will get your feedback. And if you want to have a look at the machine,